Hello, guys. What's going on?
So
Are you
Leanna
ready?
just showed up and we're just organizing. She brought food and there was conversations, but we'll try and start in a minute.
Okay.
Hello, this is.
You have to put that in mute.
I had to put my. Hello, this is Greg Mikowski from the SF Bay ACM. So I'm going to invite tonight's talk. And then down again. So tonight's talk is from static pipelines to co-evolving AI, building adaptive vision systems by Gowdhaman, the CTO of LabelBees AI. So this organization is a San Francisco Bay Area ACM. We're a local professional chapter of the Association of Computing Machinery, the Professional Society of Computer Scientists. So we were founded back in 1957, a little bit before meetup.com. We have a $20 annual membership. We're a nonprofit. You can see our upcoming talks on our meetup channel for SF Bay ACM. We have about 13,000 people that have come to our talks in the past. Once we have a talk, we host the recording on YouTube. So we have about 260 of our more recent past talks on your YouTube channel. A lot of times we'll have talks on the third Wednesday of the month or the fourth Monday of the month. I'd like to thank a couple of sponsors. One is Valley Research Park, where we have a lot of our evening meetings. They have suites for rent in Mountain View. Another sponsor is RXM. They do cloud native AI training and consulting. So if you need customized training, say that's on your site in your city in US or Europe or wherever you like, then they can accommodate. So if you need a week-long training in advanced Kubernetes, that's an example of one thing they could provide among many. Another sponsor is Front Egg. So they manage dealing with identity. So tonight it's all virtual. So please use the chat in Zoom for questions to the speaker. My name is Greg. I'll be the moderator sitting next to the speaker. So I'll watch for questions that come in and I'll ask questions on behalf of the audience. You can also use the chat for technical issues. We also like to, when we're in person, support computer science job announcements or other events. So if there's other talks or societies or meetups that might be of interest to people that are in the Bay Area that you want to share, then you can also share that on the Zoom chat as well. We have a call for volunteers. So we could use help with various things. We have about a dozen volunteers involved in different roles. I may be forward facing just because I invite data science speakers and introducing, but there's a lot of things from organizing food to finding locations for meetings to marketing promotions. So there's a wide variety of different kinds of things. We have I've had 3 new TAs I found recently for the professional development seminar coming up, so that's good. So we have quite a lot of upcoming events. So Saturday, October 25th at UCF SF Mission Bay campus. So this is near San Francisco. There's a Bay Area Science Festival That's not something that ACM is organizing, but it's something we're promoting. It's something that might be of interest. So check that out on the meetup site. Monday, November 10th at 6 p.m., a little bit earlier than usual, at the VRB in Mountain View, or you can connect by Zoom. There's accelerating startups to put enterprise Gen AI, multiple agent systems into production. And then the following weekend, we have a 2-day event, a professional development seminar that we call a PDS. So I'll have more details on the next slide, but the title is Towards Agentic Intelligence, Architectures for Multi-Agent AI Systems. So the speaker had a very, very popular talk in September. We had 360 people sign up for that for the evening talk. And so now we're turning that into a 2-day event. Later in November 19th, we have Designing for Scale, Reliability, and Resiliency, Real-World Lessons. So that's more of a computer science talk from DoorDash. Then skipping over December into January, we have a Taming Tech Deck for Platform Reliability by a Google site engineer. So that's our slate overview of upcoming talks. To drill down more on the PDS, this is our major fundraiser that we do for the year as a nonprofit. So we have an outline here of the day one that's focused on labs for the day. So we'll have a lab, like a 90-minute lab, coffee break, 90-minute lab, lunch break, and so on for the afternoon. So that'll be using Google Colab, Python, Jupyter Notebooks, things like that around building multi-agent systems. Then day two is going to have some lectures. So this is not a free event. There's a barcode on the right. You can pay for tickets at Eventbrite. Also, if you go to our meetup site and look for this event on the November 15th, at the very top of it, it'll have a big bold link to go to Eventbrite to pay for it. So we have a 20% early bird discount if you sign up early. And that's also stackable. If you sign up for both days, then you get a 10% discount. So don't delay, sign up today. So for tonight's talk, can you turn up the volume icon, just hit the X on the right of it. So tonight's speaker, the topic is From Static Pipelines to Co-evolving AI, Building Adaptive Vision Systems by Gowdhaman. So talking about traditional computer vision uses rigid sequential pipelines, and it's a challenge for edge cases, shifting domains, demands that are constantly changing. So he wants to share a vision for co-evolving AI systems where the models, data, and feedback loops grow together. He'll speak on how to harness the foundation models with active learning, few-shot, to minimize dependence on the ground truth of the data. We'll talk about how to design pipelines to capture edge cases before they become failures and use production feedback in real time. So it's a blueprint for the future of AI infrastructure. As some background for his bio, as I said, he's a co-founder and CTO of Label Bees AI, and you can see his website there. 12 years of experience in defense, insurance, and geospatial intelligence. At Orbital Insight, he led the AI engineering for multimodal SAR, EO, and AIS fusion systems. At EMC Insurance, he transformed legacy systems to AI-driven systems. And you can see his LinkedIn profile there. So if there was an audience here, I'd say have a warm round of applause, but let's welcome, and we'll switch over to having our speaker give his presentation. So thank you.
Thank you, Greg. Hey, thank you, Greg, for the introduction, and also it's a pleasure to talk to you, share my vision and knowledge with the folks here at Bay Area Sadhasivam team. Once again, thanks for the audience in online and here in office space. All right. So I'm just curious, how many of us have built systems, machine learning systems, especially focused on like computer vision? Few, I think probably in audience, we have like a couple of them. So I just want to share what are the current challenges with the current static pipelines models, especially in building a machine vision system. So a few years ago, I deployed a vision model, and that actually worked really well. And after some time, probably in a month or later, the performance dropped significantly. And there is nothing wrong with the model. Everything looks good, the environment looks good. Then when we looked into that, what's causing the problem is the world got changed. Obviously, especially when you are working with any Earth observation systems, we have to monitor what's happening on Earth. And there are a lot of dynamic operations are happening. And we have to make the model robust enough to understand what's happening here. And as Greg mentioned, so I have been working with the machine learning systems and computer vision and multimodal systems for the last 12 years, and deployed continuous learning systems for models that not only go live, but also keep getting better over the period for both commercial and public sector customers.
If you like, you can turn on the camera on your computer on Zoom.
Okay. Right. All right. So what we are going to do here is we are going to see how the system needs to be evolved over the period. And I want to share the topic about co-evaluation of AI. What does it mean, and why things has to be changed over the period, and what could it mean for the next decade of intelligence systems. So there are a lot of challenges in terms of deploying any production systems in a real world, especially where the high stakes are involved. When we are deploying any system that has to run on highly critical or mission critical situations.
You're still on the title. Okay.
So the mission critical situations are like still really a problem here. And we have to take care of this model needs to be deployed in on time and has to be improved and take care of it. So what we are going to see today is like why we need to rethink our AI systems, and what does like co-evaluation means, and what are those enablers, and insights from the field experiments that we have done, then future of intelligent systems, how that look like. And I'm going to give a few times to take care of question and answers. So for the next 30-40 minutes, we'll spend time on these sections. And if you have any questions, feel free to stop or post it in the Zoom chat or in the YouTube channel, and the moderator will take care of it. And I'm happy to share my insights here. Why do we need to rethink about our AI systems? We have built this for last decades, and even since a long time. When there is a calculator popped up, everybody thought, oh, this is an AI intelligence system. And when there is a predictive modeling popped up, oh, this is an artificial intelligence system. And there is a image classifier or AlexNet, CNN evolved, oh, this is AI, and everybody was, oh, this is an AI system. Now we have like LLMs, and we have large vision systems, foundational models, agents, Now we call this as like artificial intelligence systems. Throughout this journey, one thing is very clear. AI is evolving constantly over the period. And it's not just a single evaluation or a software component. It's actually the whole system that's evolving. That evolved decades, like other living organisms, where how this is evolving or accumulating all the changes and knowledge and generation of insights. I want to share a couple of real world examples that contributed to my thoughts on like why this has to be revised in a different way. And of course, there are multiple ways to implement this, and want to share these examples. And this actually contributed to my rethinking the approach of like designing a system over the period while I was working on my previous work and deployed the models in production systems.
I don't think your face shows up unless it's on that screen, because that's a screen you're showing for Zoom.
Okay.
If you want to put that on,
I think I don't know how I don't know how does it work.
I'm just drag it over there.
Okay.
Well, wait till it shows your face. Oh, you can just skip it if it's
You can just skip it.
okay. That's fine.
Cool. All right. So this is actually a simulated data, but it's not the real production data, but actually the production data appeared like this only. I deployed a risk detection model for identifying highly risk drivers for specific insurance problems. The objective is like to drop 5% of high risk drivers who actually causing a lot of losses to a certain book of business. And we have to constantly monitor who are all those risky drivers and how this model has to be fixed and dropped for identifying those risky drivers who are in the book of business. The model is deployed really well, and every day we'll go through that. We get the alert about what's happening and how many drivers have been like insured and in the book of business, and during renewal how that will look like, and if there are any drift in the model, if it is, let's say, more than 5% of the drivers are like rejected, then there is something wrong here. So we need to take a look into that. So again, the model is still the same. Everything is remains the same except the data in the model. So data got drifted in productions, and the model still remains the same. So we have to go and adjust the model and fine tune it again or fix the pipeline. Another interesting challenge which I faced years ago again. This is another latest one. Countries are deploying inflatable objects to escape from scanning or like to deceive other countries or adversaries from what's happening. So if you look at the objects from space, the objects will appear as like a real object. But when it comes to the real world, it's actually an inflatable objects. So how does it work? And it just start with the simple truth, how an object appears in real world. And our real world is moving faster enough, but our models are static. We deploy a model, and within a weeks, the accuracy will get dropped, or not only accuracy, different problems and different constraints as product and engineering metrics, they will adjust the criteria. Like for example, in this case, hey, I need to know what's happening in this particular adversary target area, and how many objects are there, or how many fighter jets are there, and what's happening if people are like moving away from one location to another location. Then this is actually a mission critical situation. We want to know what's happening here.
A question from the audience. Somebody was asking, what do you mean by data drift? Can you give an example? If it's all right with you, maybe I can answer that. So think of a model as fitting the training data. So like when you go to a store and you buy an object that has shrink wrap plastic that fits tightly around all the curves of your whatever the object is. So that's like a model fitting the training data. Now, if behaviors change over time from week 1 to week 2, if you're selling something, then your customers are seeing other sales from competitors, or there's a new product release, a new phone comes out, something happens in the dynamics of the market, then there's a change in how people make decisions. So that's data drift. That's the behavior change over time. Now, the model that fit the training data, well, it still fits the training data. The model hasn't degraded. The model's ability to fit the training data is still just as good. It's just that the behavior has drifted over time. And so now you need to either update or retrain your model or refresh your model on the newer behavior change. And so sometimes, when you're creating your pre-processing, then you think of how can I create my pre-processing so my credit card attrition model will work any time of the year, whether there's a Christmas spending spike or not. So sometimes there's things you can design in the system to be robust to some fluctuations. But other times you just have to do a retraining. So it's very domain specific.
That was my question, but I just wanted an example of, have you seen something in the real world where it's changed in 3 weeks, where it's just dropped to close to?
Yeah. Another question was, what's an example? Have you seen another example of where it's dropped in, say, 3 weeks? And I would say banner advertising. Banner advertising, when I've worked in that area, they would retrain the models every night. For targeted marketing models for mailing, like if you have an insert in your credit card, then that model might get used once a month. And those models I would track, and maybe they'd stay in production for a year and a half or 3 years. If you look at the slowest, most stable was canceling your insurance. So you get an insurance premium payment every 6 months. And so people don't think about evaluating changing insurance until they get the bill. So if getting the bill is slower, then the possibility of canceling or switching to another insurance company is slower. So those models could go on for 3 or 4 years. So that's an example based on how dynamic the data is and the behavior change, then that would indicate how often you need to retrain your model. But there's the same process of tracking data drift.
And social media, that's another very good example, like where the behavior of the users will change. Suddenly, like there is a trending data, trending video, like user behavior of like, okay, their interest got changed. So we have to like retrain the model and deploy faster. I think once the behavior is basically like the model needs to adapt to the real world behaviors of users. So that depends upon the problem, depends upon your domain. This has to be retrained. And how often it has retrained, it's dependent on how often your data will change.
And fraud is the most challenging, as I've run a number of fraud detection teams. And so then that's an arms race where they're trying to change their behavior to not get caught. And so then it's adversarial relationship, not just what's going on in the latest meme on the internet. So then that's a very different kind of situation and a different kind of response.
Yep. Awesome. So what's happening today in our legacy AI pipelines, and how many of us have seen this picture? So any model development involves like 6 to 8 different steps, nothing more than that. It's a conveyor belt. And how this is working is the team member, the product engineer, the data engineers, the model developers, and business owners, they are working on their own siloed environment where they know exactly what they are doing on their own, on their environment, on their own work. But often the communications between cross-functional team is like lost somewhere. Either they write in design documents or a project documents, they write in some Google Docs or in a Confluence page or put it somewhere in Notion. So we have been following this linear process for long enough on like collecting your data and preparing your data sets, train the model, benchmark and deploy, and that's it. So you can say that, oh yeah, the model is deployed in production. But there are in real world, this will change over the period, and especially for like vision systems and robotics and earth observations. It's like we are steering our ship by looking at yesterday's map of what do we have, or what did we face yesterday, and that's not going to work. And the pipelines are designed in this one-way conveyor belt is really very static, and we optimized for the control, but actually it's not optimized for the change, or not optimized in a way to adapt to the environment that is changing over the period. So, and as a result, we see a lot of latency here, and the real world feedback comes too late, but our model already failed in the production environment. And the cost of retraining or fine-tuning is expensive, and we have to start from a scratch. And always the ground truth is a bottleneck, where people are, especially the model developers, will think, oh, I need more ground truth data. But really, you don't need more ground truth data. You just need to know what is causing the issue of the model performance dropped and what is needed in that particular data. So when we collect the ground truth data, it's not just, well, for object detection, you can go and do dry bounding box and add an attributes, you got the data. That will solve the problem, but not the entire performance. Let's say you may get a model quickly by 60% or 90%. Then the going from 90 to 100, that's actually a last mile challenge. What we see in autonomous industry, that we need to tackle that. So imagine how this will work when there is no siloed environment where every team member will work together and the data needs to be flowed among these teams. When I was solving this problem in my previous work, one day it hit me like, well, it's not the model only is actually causing the problem. It's actually the entire system. So the model is not the AI that what we call, but all the things, the system that actually surrounding it by this huge concepts of around like data, environment, and your human knowledge, machine learning models, and the knowledge base, what the ground truth information about what's happening in a real world, and the infrastructure, and everything that actually combined together, they all co-create the intelligence that what we are looking for. So what if we stopped building the models in an isolation and started building an ecosystem that can learn and evolve as a whole? So we need a system that can learn from humans, and similarly, like humans can learn from the system. And we both evolve as a living organisms. The system encompasses all the elements that influence how the AI is built over the period.
So just as a comment, the system is what demonstrates the most intelligent behavior.
Yeah.
It's not limited just to what's in the model by itself.
Yep, that's true, totally. So if you take a look at what do we do with current model development approach versus how our dynamic world is evolving, it's all linear. What we do with our model development is like one-way conveyor belt, or sometimes there is some loop, but not actually fully evolved. And the process of developing these models and our environment they are not actually correlated, in the sense our world is evolving faster, but we are trying to fix the issue that we faced yesterday, but not in a real time, or at least in a near real time. And this legacy pipeline versus our evolving world, it's not aligned world. and it's actually completely broken, the one-way conveyor belt method of developing the model is already broken here. And how do we fix it? Think about, yes, the components, especially like data, knowledge, model, workflows, feedback loops, and things will evolve over the period. And that actually comes from the concept of like co-evaluation of what's happening in a real world. So we call this approach as a co-evolving AI system. Instead of one-way conveyor belt, a living loop where the knowledge about the real world, the data, the model, and the feedback, it continuously shape each other and evolve as a whole. When the world changes, maybe let's say there is a new construction is happening. Oh, there is a road got blocked, or there is some new foreign objects we found on the road in the autonomous car. How this autonomous car can synthesize that information and take a decision, or how it learns from humans and intelligently navigate from that obstacles. So the system has to learn and evolve over the period. And in co-evolving systems, training and deployment, they are not separate. And we treat as together, and we evolve it as a continuous learning pipeline. So how this works actually in terms of the principles? What are those principles? And the principles of to make a system robust enough and evolve together with the dynamic changes in the real world, it has to guide the system to learn. The key principles are parallel evaluation between your data, your model, and the product. When you say the product, the entire ecosystem. And the feedback loops, there is no boundary between your development team or a production team or a product team. The feedbacks from the user, feedback from the environment, feedback from the data, and feedback from your knowledge has to be continuously joined together and feed that input back to the model and also to the human beings who are actually developing these models. And adaptive learning in terms of focus on human effort, where collecting the ground truth data that is uncertain, and that's going to push the needle of the model performance to the next level or the entire ecosystem to the next level. And it's driven by the contextual intelligence about your ontologies. Ontologies are like things that evolve over the period, and you know about like how a certain object will behave, their relationship, their taxonomies. All this knowledge has to be captured in some sort of data sets, and this knowledge has to be transformed to your machine learning model or computer vision systems that can understand the context of where this model going to run in a real world. And the observability of your model, and also most important in terms of where this model will cause an issue, and every event that actually is, or like every event or a scenario where the model failed, it's a learning signal. And these key principles will lay the foundation of a co-evolving system that learns together along with the real world. There are scenarios where sometimes we have to even change the environment. Like, for example, when you deploy an autonomous robot in a warehouse, we have a full control of changing that environment. We can design and build the warehouse where the system can work at high performance. So the feedback is not single directional, it's a bidirectional, or you can say the multidirectional. You can get the feedback coming from the real world, or you can also have the feedback send it to the real world or the humans.
A comment on the adaptive ground truth, focus on what matters. So some vision projects I've worked on, the rare case is really important.
Yep.
So worker safety at a construction site where somebody falls or somebody has an accident, that's a very rare event. If you think of 100 people at a site working for 100 days and an accident happens once over 2 minutes. So you think about the number of 2 minutes of video of a accident versus all the minutes of video of non-accident. When you're training models, the models need practice.
Yep.
The more they can practice on the rare high value cases, the better. So like in 2019 and 20, for that project, we outsourced to a firm that was using gaming, like the Unreal Engine, to generate some synthetic data
Yep.
for some falling conditions. Because we could stage some things, putting on hard hats and vests and things like that, but not injuries.
Yep, totally. And synthetic data, that's a great alternative for identifying or like finding a rare events or simulating a rare events and give it to the model. But there are other challenges with synthetic data as well, like the dynamics or the rendering of synthetic data needs to be as close to the real world or like real data. Otherwise, your model will work on your synthetic data 100% awesome, but when you deploy in real world, the model will flatters. So synthetic data is still, it will work, but not all the time. So there are methods where you can optimize it, where you can put your synthetic data on a training set and control your model to learn it on a real data. So that's where we use like mix of both real data sets and synthetic data sets, especially for capturing rare objects. I can give you one example that I came across in my past. There was a brand new drone that was deployed by one of the advisory, and that drone blueprint or any of them, it's not at all available in online. It's luckily like it was captured in one of the satellite imagery, and we have to generate more object like that. And obviously the way to go is, well, use a synthetic data sets, use a Unreal Engine or a graphics engine to generate an object. So which is basically you create a 3D model of your target objects and your background, and fuse your foreground objects and your background and generate multiple images and data sets. But still the model will fail. That's where the expert sauce and experience that we needed to optimize the model to run on a real world.
And that's not just limited to vision projects. Like when I've done fraud detection for finance fraud, I might have a moving window of 6 months of data over hundreds of banks and credit unions. And so some data would roll off, but if what would roll off would be a fraud case, I would capture that and add it back in a plausible fashion. So it's actual data. I might have to do some adjustments just to have it to fit in a plausible setting.
Yep.
In the context. But that way I could keep all the wisdom, and I would want to focus not just on an exact fit of one con, but I fixate on like the 10 elements of the con.
Yep.
That could be reconfigured in different ways.
Yep. Totally. All right. Okay. So I want to share a blueprint. This is what we call, especially at level Bs, a blueprint of living AI system. And the system has like several components. You can say that as aligned with our traditional conveyor belt, but how these components are like correlated or how they are talking to each other and learn from each other, that's actually the game here. So we have like your data collection process, then we have to curate the data or enrich the data. Then there is a knowledge base where a centralized repository where we capture all the informations about what's happening inside the model or inside the data or in the real world. Then we have like expert input. It could be your content manager or a domain experts who really knows about the problem, or even like there are times where I worked with the experts like veterans, and there are times I worked with the risk improvement personals in insurance where they really know about like how the roof of the building is structured, what materials they use. So all these informations are like, it's not just you draw a bounding box based upon the guidelines or draw a pixel brush based upon the guidelines. It's more about like nuances that needed. And this goes back to my hypothesis. You don't need a huge amount of data. You just need the right set of data sets to build a better performing model. Then we have like feedback loops, data preparations, then have to monitor the data on the model and also like deploy it. And this continues. And everything is based on the real world, not necessary to be a real world. Some uncertain situations or rare conditions, we have to create a virtual environment as well. So basically the ecosystem is learning from real world and the virtual environment. And we will unpack each component one by one, and we can talk about each component. I also would like to remind, this is a living blueprint. That means it evolves over the period. And when we started this a while back, it was very few simple components. Now it's like has too many process and steps and methodologies that we are following. And I purposely ignored the infrastructure and all the other components and focused only on like model training and model improvement and continuous learning and continuous evolving. So knowledge base. So what do we call as a knowledge base? You can take as knowledge about the real world, the problem that you are solving. Let's say if you are building a vision system for like senior people falling detection. So we need to know what are the scenarios where we'll be deploying it. I can give you one example. When I deploy a system to monitor slip and fall hazards for a worker compensation insurance. So I need to know what are the scenarios where there are like slip and fall hazards will happen. Someone dropped the water, or hey, someone dropped the banana peels, or someone dropped an obstacles. Even there are scenarios where if the staircase of if a staircase in a building that doesn't have like color contrast signals, that's actually another edge case. This will cause someone to trip and fall. So the environment knowledge, the scenarios needs to be captured. But another example where we need to know about the debris on a roof. What will cause debris? Like probably someone throws some junk on the roof, or leaves that fall on the floor of the roof. All those scenarios will cause debris, and it will change. We cannot say that even a broken cable that will cause a problem for an insurer. So all this knowledge needs to be captured somewhere in a centralized repository. So your product and the model engineers and the content developers, they can understand the concepts and can define the right problem, and also they can define the right business metrics and engineering and performance metrics they need to take care to design a system. In terms of data collections, once we have collected the knowledge about the problem that we are trying to solve, then we design what data that we need to collect to solve the particular problem. In the case debris detection, the broken cables, we should call that as a debris, or objects that are on top of the electrical units in a building, we should call that as a debris. So these informations, once we have the knowledge of what are the target objects, then we can go and collect the data. Either there are times where we need to go and collect the data from real ground. I can give an example where I went to a building and just had a drone pilot, and we just fly the drone over the buildings and collected different informations and collected all the nuances. But definitely we cannot capture all the debris categories and the scenarios. So that's where like we bring in a synthetic. Once we collected the data, now we know that what the business metric will look like and how that will impact the model performance in productions. And what will
Just a curiosity, on the application, what's the business use of identifying debris on a building top?
Oh, that's a great, actually. So this is for a risk improvement purpose. This is for insurance, commercial insurance, where we want to estimate the risk or exposure we call in the insurance industry. What is the exposure that we are insuring this building? How much this is worth for it?
So is that a potential fire hazard? Okay,
If any hazard happens, and what is the risk of that hazard will happen in near future? So if I'm insuring this current building, as an insurer, and from a risk improvement perspective, I need to know what are the risks associated with this building. Low-hanging vegetations, low-hanging cables, drainage blocks on the roof of the building, and the roof floors, what materials they used for that particular roof. All these signals
okay.
will decide the premium that we should charge for that particular building.
Okay.
So once we collected the data, then we'll get into enrichment, where we curate the data sets. Sometimes data might not have all the information we are looking for. Like for example, in Earth observations, we have like tons and tons of data coming from space. I think on an average, we are getting millions of screenshots from different constellation of satellites. And we need to identify the target object that we are looking for from that millions of data points, like petabytes of data. And imagine one snapshot of Earth, depending upon the satellite resolution, we'll be having 10,000 cross 10,000 pixels. And that will end up, if we convert that into small images, it will become like millions of data or millions of images. And we need to know what data point will help us to build the model. Certainly, we can throw all the data points to put it into the model and create the data collection or ground truth collection process. But again, there is a trade-off. We don't have a time, or we don't have enough time, we don't have enough budget. So all those factors needs to be considered to narrow down the data points or images in terms of, depends upon the problem. In the multimodal systems, we have to fuse the data from image, and also we have to fuse the data from other structured data sets. So we have to curate what data that we are looking for and pick the right data points that can help us to push the model performance to the next level or towards our North Star metrics. Then expert inputs. This is where the human knowledge is most precise and important. It's not something that model can learn by themselves. Someone has to put the seed. The seed is actually coming from the humans. And to close the last mile challenge problem of moving from 90% model performance to close to 100%, that really needs human level intelligence to feed the right data and correct the error in the model. Sometimes there are scenarios where even a normal human cannot distinguish between target objects. If you are going with the fine-grained level, we cannot even find that. So we have to use different sensors like red, green, and blue channel camera, or we can have to go with the infrared, or we have to go with the like more spectrums of data that can identify the right signals from the target objects. And once we have that campaign started, hey, we have the problem framed, we know the knowledge that we want to collect, and we have the human verified that yes, this problem can be solved by humans, and we can differentiate the target objects, or we can identify the target objects from a given sensor. Then we can spin up the campaign, go and collect the ground truth informations. Like I mentioned, we don't need huge amount of ground truth data. We always start with something small. Let's say, based upon the problem, you start with for an example, you can say 1,000 images or 500 images, just fine tune your model. Then you can bring pseudo labels, use your model to train on the given small amount of data. Then you can use the same model to generate pseudo labels. Pseudo labels are, you generate the predictions using the model that you already have. And of course, it requires a lot of quality control process. through programmatic quality control or expert in the loop, or even you can have a AI, another models, or even you can use LLM as a judge where you can identify, hey, is this the right data that we are looking for? Is this aligned with my bounding boxes or aligned with my pixels? You can do all the quality control process. And again, through your campaign or while we are collecting a ground truth data, we can detect edge cases. I can give you a lot of examples especially when we are working with the geospatial, because depending upon your sensor resolution, your object will look like 2 pixels or 3 pixels. That's it. There are cases, imagine a car, if it is in one, for the conversation, if it is a 1 meter pixel camera, any 1 meter square on Earth will appear as 1 pixel on image. So the resolution will vary based on based upon the target objects. Like the resolution, like based upon your sensor resolution, the dimensionality or the visual information about the target object will vary. And those edge cases definitely would not be available in our knowledge base or ontology. In that case, where we have to coordinate with our experts and identify, hey, what is the problem here? And sometimes our experts will give input to our model engineers on, based upon your ontology, there is something is missing because a new object is popped up in a new collection of data. So then we have to quickly reiterate our strategy of ground truth collection and focus on what really matters. There are cases where we have to enrich in terms of collecting more attributes. For example, how the object is occluded. Are there any object is causing an occlusion on a target object? Or are there any object is causing any shadows? And what is the dimension of a particular target object? So all these attributes has to be captured in order to feed that knowledge back to your model through these attributes. And if you look at once you collected the ground truth, everything looks good, but we cannot, as a model developer, we cannot go and take the data blindly and put it into the model training. So that's where like your model developers, we asked to take a look at the quality control process and see how does it look like. Just do some statistical test on your ground truth collection, ensure the quality is meeting the needs, ensure the attributes or the characteristics of your target objects are captured in the ground truth data. And if that meets a requirement, very good. Let's go and do the simple model training with foundation model or some base model. Again, depending upon the problem, we may have to start from a scratch or we just fine tuning. Fine tuning is basically we are freezing all the layers of a neural networks and train only on the top layers. Your problem domain and your amount of data that you have, based upon this, your training strategy will vary. And once we have collected the data sets, I think I'm running out of battery. Just
power. There's a power strip right here.
Yep, I can just do that. Just all right, I'm back.
Yeah, the 3 dots at the Mori on the far right, you get rid of it. It's hide floating meeting controls down one, I think.
Awesome. Thank you. Cool. So once we collected the data and we just start the experiments, as a model developer, like we try a lot of experiments in parallel. There are scenarios where we train like multiple experiments in parallel and see like which one works better. And these experiments are guided by the hyperparameters, guided by the model performance on a given small sample of data. And any model development will always start with the small data sets. Imagine, I think there were time I was training a large spinning up a model with a large amount of data, you can think of like in gigabytes, like 500 or even close to like more than 500 GB of data. And this will train for a week. Before we spin up huge amount of volume of model training, we always try with some simple approach, like take some sample of subset of sample from the volume and identify like how this model behaves and what does the pipeline look like, and what would be the model performance or the model setup will look like. Once those informations are validated, then we spin up the large volume of model training or the period. And that comes with the model training, experiments, benchmarking. Once you have the benchmarking, then we can go on, do the validation, do some A/B testing. Once the testing is done, we put it back on our validation or approval process. Once it is approved, we put it into the production. But before even before we put into the production, like we just do A/B testing on like how the model that we have in hand right now versus the one that is already running in a production behaves. And based upon the benchmark and the performance, we will say that, oh yes, now this is the time to flip the model. Then we just put the latest model into the production. And not only just training, but also in terms of like monitoring how this model is behaving over the period. It's in terms of the real world, the performance, and any new foreign objects evolved over the period. And there are times where we have to force the model to learn some real world information or like some real world nuances. I can give you an example. There were time we need to do a fine grained classification on an object along with their attributes, the dimensions, their characteristics. In that case, it's not like simple classifier alone, along with the bounding boxes, and you can do the object detection where you have the class labels and you have the bounding box information about the target object. That didn't work really well. So what we have to do is we need to add additional attributes, and we have to do some surgery, like which is basically take an existing network and add additional heads on top of the existing ones. Then add a loss function that can penalize the model for certain characteristics. Like, let's say if you want to know a fine-grained classification of, I want to classify what is the, for example, the color of an object. So in that case, like we would have add a classifier, or there are scenarios where you don't even need a complex model. You can add a simple computer vision problems or like operations by looking at the hue values or color pixels. You can do the math and you can calculate the necessary information that you are looking for. As a model developer, you don't have to always think like this can be solved through a deep neural networks or even a machine learning. Even a simple computer vision operations can solve the problem. If you look at this,
earlier you mentioned data drift. Do you have any kind of data drift detection in this flow chart, or maybe something coming up for the vision? You know, maybe if you're detecting 36 objects and one object is going from happening in 1% of the time to 10% of the time, or the RGB distribution of your label is changing for that object.
Yep. No, certainly, like the data drift happen in a multiple scenarios. It's not only changing the object, new foreign objects will be popped up in your population, and sometimes your sensors might be an issue. For example, I had faced the same several issues. My the satellite image processing might have messed up, or they added some different algorithms for the processing, and all of a sudden, like visually the image will look like good, but those histogram of those pixel values might have shifted, which is entirely different from my target objects, or entirely different from my training data sets. So in that case, like, oh, the histogram got shifted, or like for example, some pre-processing methods, they might have changed. So we have to calculate that, okay, how is the distribution of these data sets look like? And if the distribution is changed significantly, yes, then that will trigger another signal to the model developers. Hey, something is got changed in the production. You have to go and retrain it. So we have to take a look at what caused change, what is an issue, and we have to either should retrain or just fine tune it, or it just a pre-processing pipeline got messed up.
So is that a manual process to find that, or do you have some automation in your error analysis?
Yep.
To detect for, now I have higher error rate in class 14, so look at that.
Yeah, so we have automated process, like a couple of examples are, one is like those distribution mismatch, then another one is like significant drop in model confidence, or like significant change in the model confidence. And these are like some of the clues the triggers that there is something wrong in the production data.
Sounds good.
Yep. So what are all those enablers? Like why?
A remote question from one of the audience members. How does this thinking differ from TensorFlow pipelines, TFX? Or is this your extension to the TensorFlow pipelines?
No, not really. So it's not an okay, if I go back, so if you look at this, it's not an extension to TensorFlow pipelines or not. It's actually a thought process, how the entire ecosystem, right from your production to a model training to your data engineering team should operate, and how the data should be flow between between the teams across your entire ecosystem of your product. So if you look at that, when you go back to your static pipelines, it's a single one-way conveyor belt where one process is done by, let's say your product team will design your requirements, your data engineering team will design your data collection process, your model team will look for like focus only on the model, but there is no intercommunications happening. But in the co-evolving systems where all these teams are working together and the knowledge is flowing between, a constant knowledge is flowing between the teams who are working in that.
So in a way, it's kind of like the agile process. You do a common use case first, then you, in a first sprint, maybe later sprints, you add, oh, let's do these new features, do this adaptation across the different teams. So it's like the different teams are kind of adding or doing more adaptation, adding more complexity over time.
No, it's not an agile method. It's like, think about if you're, okay, think about if you're framing a problem, if a product manager is framing a problem, and how do we ensure that the problem is actually the real world, that's actually the defining the real world. When you say how many attributes are captured, or what is that the characteristic of a target object? Like I'll give an example. Let's say I want to detect a roof of a building, and as a product manager has to know about how a roof of a building will look like, and how does it evolve over the period, or different countries or different state have like different architectural design on the taste. Based upon the environment, the roof materials will change, the structure will change. So all this knowledge has to be captured. And where do we capture this information? Your product might have good knowledge, but your risk improvement, who is actually the field expert, might have better knowledge about what's happening. And how do we keep these folks to be on the same page? And of course, not only the human, but your model also has to learn from this data. And this is constantly evolving. So in the sense, if you look at that, the knowledge about the real world and the human experts continuously giving a feedback to the model, and also the model is giving a feedback to your human experts.
So just to reiterate back to the user question, how does it differ from the TensorFlow pipelines? The TensorFlow pipelines would be a small 5% of the overall system.
Yep.
The overall system is doing adaptation across many different departments or specialties of people over time, over the project duration, and you're iteratively improving.
Yep, that's totally true.
Okay.
Okay, let's unpack how how a co-evolving system is being designed and being used in most successful teams. For years, like the idea of continuously learning systems sounded impractical, and we were not able to think that this co-evolving system can be designed or can be built. But in past few years, we had seen several foundational shift in terms of like how the computing, even a computing infrastructure is evolving, and we have like foundational models such as a clip, or even SAM grounding Geno are like evolving a lot, and large language vision models, it's also evolving, and there are a lot of changes making us to think it's possible to do that co-evolving system that can learn together from a real world. And let's start with foundational models. Foundational models are like, these are all the models that have learned from rich set of visual or textual prior knowledge. Instead of starting from a scratch, we take these foundational models and fine tune it, and that actually make your downstream process and applications adaptable. Several foundational models are available, especially for vision systems. You can have like a segment anything models, grounding Geno, or like that is for video models. We have like JEPA from Meta. And these foundational models are using a self-supervised techniques to learn from the data. So self-supervised learning and few shots methods, these are like the models that learn from the structure of your data sets, especially for self-supervised one. It learns from the underlying structure of your unlabeled data sets. We don't even need a ground truth data. Instead, like it learns a representation, like spotting the patterns in a given images or a given problem, or asking like where this model will uncertain about the scenarios. That turns every thoughtful feedback about the challenges in the vision system into a signal that will create a new neurons for a neural network. The third one is like unified data structure. That's where like all the components and the pipelines are on the same page, and the data is continuously flowing in a bidirectional way. It's not in a siloed environment. And in a traditional pipelines where data lived in a silos, where you are labeling in one places, your content team will do the quality control, your data engineer will focus on collecting the data sets, giving it to the model engineer, then model engineer will train the model and give it back to the product. And when you put it in the production, everything will blow off. So now we need a unified infrastructure and backbones that can take each stages of the model development process and enable the data to flow in a real time. So your model and the knowledge base, humans, will evolve along with the real world challenges. And the fourth one is like experts, where we need a humans to give input to correct the model issues and validate the models, and also like give a real-time feedback on what is causing an issue. Feedback from a human is not just a separate phase of a problem. It's actually the real-time information that we need to feed to the model that's already running in a production. And the fifth one is like agents and memory. With help of LLMs can synthesize your product knowledge and can synthesize all the knowledge that we have captured in your knowledge base. Imagine, let's say you are a data engineer is trying to build a roof type detections, and they might not be a risk improvement expert who is seasoned and experienced in identifying the risk associated with the given building and roof. How do we transfer the knowledge from a risk improvement professional and give it to our your model engineers or data engineers? So that unique knowledge transfer needs to be happen. And in order to do the transfer, we need to retain that knowledge somewhere. That's where you have the memory of like storing that data along with the rich set of informations in your knowledge base. Then you can have an LLMs that can summarize, or you can have a RAG pipelines on top of it that can guide your model developers, data engineers, not only like model developer and data engineers. The model that is running in a production can also be guided by these systems. Like, for example, hey, I classified this as so-and-so. My confidence about a particular object detection is dropped significantly. Then we can feed that signal back to why the performance got dropped, what caused an issue. Is that a drift in the data, or is it drift in the model, or what is causing a problem? So all this knowledge has to be like continuously flow back between the components. Last but not least, the infrastructure, the elastic infrastructure that is needed to build an orchestration frameworks that can continuously deploy the model, can continuously monitor and improve the deployed models for the period. And retraining is not a once in a quarter event. It's actually a pulse of heartbeat every day, or like daily rhythm of what's happening in the ecosystem. Is my model learn that information or not?
Sometimes I would use model refresh as something that's more automated, or it's just change the same training code on newer data, and on fresher data. I might call that a model refresh. I might call a retrain as explore from the start, do error analysis from the start. It's almost like building a new model, or closer to that kind of. So sometimes I might use those different terms, a refresh versus retrain, as far as what might be needed to update.
Yeah, again, so we call fine tuning it.
Yeah.
Technically, we call this as a fine tuning it. We don't have to retrain the full, like we don't have to like train all the layers of the network. We just focus on only few layers. Sometimes if you have like huge amount of data and huge amount of budget and infrastructure, just go and train all the layers based upon the problem. So combining these components, where we call that these components are like this shift of foundational self-supervised and unified data infrastructure and your experts and LLMs and memory that actually transforms our static conveyor belt, what we do in the legacy pipelines, into a co-evolving AI systems. The system is the one that has to evolve, not just a single model. The model is, without a system, the model, it's not an even can adapt to the given environment. So people might think, oh, well, if model is evolving or learning by themselves, or the system is learning by themselves, then what will happen to the human, right? Even with all this automation and self-learning and foundational models, there is still one layer is needed. That's where the human layers are. In traditional pipelines, like human labels, label the data and start and evaluate the results at the end, but actually it's not the case. In a co-evolving system where the system has to identify what the feedback will look like and learn from humans. Think human will act as teacher, or someone who can identify or give feedback to the model and the system to identify those edge cases and validate that information. In co-evolving systems, humans are like not just labeling or not just collecting a data, they are actually teaching the model. They are also learning based upon what's happening in a real world along with the model. So the feedback is going to the data and the model and also to the humans. And this is a simple as an example of like how a systemic intelligence will look like. And it's built by like layers of multiple layers, like our infrastructure layer, storage, building blocks, intelligence layer, and interface layer. The goal is to make the models smarter in isolation. That was a legacy pipeline, what we have been doing, but that's not working with today's world. And we need a system that can make that intelligence that is evolving with the dynamic changes in the real world. And every data point and every feedback signal or every error report that we produce based upon the models, it's becomes a part of the living organism memory, and we need to preserve that and give the feedback or give the continuous flow of information back to your ecosystem. And I want to iterate on like building blocks. The building blocks does actually contributing to make the system feasible, and we can achieve this, and we have tried it out and it's working out for us. So foundational models, your training frameworks and evolved frameworks, all this has to be like connected, interconnected, so that it requires a less human interventions. And the feedback loops, it has to go from bidirectional, not only just from model to a data, but also from data to a model to your humans and to your real world setup as well. Then frontier models, you can name it, all the LLMs and along with the LVMs, or even like vision action models, where you can use it to fine-tune your fine-tune them for your specific problem. But there is a challenge here. We don't need always the foundational models to run it in a production, because that comes with a cost. Depending upon your model size, you will incur latency. You will also incur a cost in terms of computing cost. A smaller model that runs like in one second for 1 million images is cheaper compared to your foundation models that's still going to run on a H100 hardware, but you will end up paying huge amount of bills. So your business metrics also needs to be important when you design your ecosystem. And a couple of insights I would like to share about what we learned over the period. And this is personally from my experience and what I had seen in the past from the system I deployed. That gives a motivation towards why the static pipelines won't work here. Which is basically the data is evolving faster because of your real world is changing faster, but our models are like not adapting to that pace, and real world conditions are changing. And what we have to fix it, the system should adapt continuously instead of waiting for retraining. And evaluation is possible only when our system learns and keep the pace with the real world. And edge cases are the real teachers. Like I mentioned, we don't need all the data to train the model. You just need to find those edge cases for your specific problem. And the model will fail, not in common cases, it actually will fail in edge cases. And we have to curate and identify those edge cases and prioritize them in your training data and identify those rare events, because every rare event will form a new neuron in your model that is impacting your model performance. And feedback is most important, and it's actually most important than your labels. Human corrections or override or contextual notes, everything that feed as an input to your model. The challenge is like how to transfer the data back into your model. That's going to be the challenge. So that's where you need to do some network surgery or identify the right loss functions or use ensemble of models, combining that to produce right information that we are looking for to create a real intelligence that grows over the period and how the system will evolve after the deployment. And what do we get out of it? What we had seen is the cycles of model ideation to a deployment is actually reduced from 3 months to 2 weeks. And we were able to collect the ground truth data along with the pseudo labels and the foundational models and human input in less than a day that we are looking for. And our team efficiency has been boosted 50% consistently. And we are like better customer experience because we were able to identify those edge cases and failures before even it hits the production or before even it hits the customer projects. And that actually earned the trust in production of our models and our user experience of our product. And what we learned and unlearned in this journey is treat system as a whole, that's as a unit of our intelligence, not just a model. And the last mile challenge of moving from like 90% to 100% that's still really a challenge. And we need to fix the gap by looking at the co-evolving system that can close the remaining percentage and collect the feedback as early as possible and do not wait for the incidents. Sometimes we wait for, oh, the real edge cases is failed or we didn't even find that. That's true, actually. We cannot find all the edge cases because the world is dynamic. It will give a lot of surprises. We cannot capture all the surprises. Then collect less data, not even more, and basically collect less and more on your existing data sets and try to find that uncertainty and have a real world knowledge and data and feedback, which is most important. And the smarter that information is, better. It's not even like huge amount of your need or like the ground truth work is required. And the best data sets are the one that keep on changing, that keep on evolving over the period along with the real world. And most importantly, this evolution is never end. You have to keep on iterated over the period and make this model consistently updated with your real world challenges. And we had seen like the most successful teams are like building evaluation pipelines. They are not just building training pipelines. Training pipelines are like just one time and forget. We need evaluation pipeline. That pipeline can learn, or the components can learn from the real world and evolve over the period. And how the future of intelligence will look like, because we are entering into the phase of real world where the intelligence is evolving and our systems and the model needs to also adapt according to this. We are entering the phase of AI systems where we'll learn from different modalities, humans, and ecosystems that continuously evolve and contextually learn and collaboratively work together with humans. And this is a living organism, and that's our North Star that we are looking for. And our infrastructure should be designed in a way that it can serve the system and it can co-learn with our humans and the real world. And this is our next frontier, where we are building an ecosystem that can learn as fast as the world they observe. And with that, I would like to end with an invitation of the co-evolving AI is not just a single model. The whole system is the intelligence that we are looking for, that we want to achieve. And if you are experimenting with this, adaptive workflows or self-learning models or any of these co-evolving systems, I'm happy to exchange notes. And this movement requires a community of builders, researchers, and dreamers. And with that, I would stop and answer any questions. Think about your own projects where you could make your workflow pipelines that can evolve in real time, and your knowledge and feedback is trapped, that you can make it better to flow freely to build the system.
So if there's any questions from the audience, go ahead and type them in the chat. I'll be happy to read them to the speaker and he can answer them. So you're using a lot of vision models. You're also talking some about LLMs. Again, LeCun was saying that LLMs aren't enough for world knowledge, that it helps to have, if you can have a world simulator that kind of knows the 3D rules and physics, systems would be, have a much better understanding
Yep.
than just being trained on text alone or just on
Exactly.
images alone.
Yep.
Any thoughts or feedback if you want to kind of riff or discuss that?
No,
I mean, it's not that it's easy to do with the
Yep.
tools we have,
Yep.
with the vision models we have,
Yep.
but it's you know, in the last section of future.
even with the vision models, like the models can learn only on what is in the data set,
Right.
right? You cannot learn how the real world look like. So a single model alone or like a bunch of models alone can solve this problem. We need each and every component that is designed in a way that can contribute to this whole ecosystem, like literally how our human brain works. A child, when there's a child is evolving or like growing, it learns from experiments, learn from practice. It needs a auditory skill, needs a vision system, logical thinking, reasoning about why certain actions are happening. All this components actually framing the human intelligence. So that we need to design in artificial intelligence as well. I certainly agree with him. What?
It's like we have some models for the eyeball, some models for the eardrum.
Yeah,
We have
exactly.
some models for the text and language.
Yeah.
But then we don't necessarily have, I don't know if it'd be some kind of graph model or 3D world simulation
Mhm.
model.
Mhm.
You know, maybe some kind of simulation system.
Yep.
That would be like a 3D video game world
Mhm.
that you could, you know, some of the new Sora 2 models where they're now able to, from a text description, create a world and navigate within that world are really impressive, even for short video clips.
Yeah, that's true. But we are not in the position. We are
But
not
that's
at
a
the
generation gap
exactly.
detection.
Yeah, that's true.
So that, you know, I don't know if there's something there that we could connect to as is trying to build it there. It seems like there needs to be some other component to build the 3D data structure that object A is on top of object B, which is,
Yep.
you know, underneath object C, just kind of that graph relationship, maybe
Mhm.
some kind of graphical reasoning system.
Yep, totally agree. So I'm glad you brought the point. So if you're building a co-evolving system, it's not just only like for a vision components. What we are having working on it, like, yeah, we need LLMs, we need a large vision models, we need a graph understanding models to transform the real world into a knowledge that machine can understand and can synthesize, establish a relationship. All these components can contributing to the intelligence. I don't think we can achieve that with these components. I would say like there are a lot of unknowns as well, and which we cannot be factored in. I think that's the direction that we are going, like how to factor in those unknowns and how to transform that data back to these models. And certainly like a bunch of models alone can achieve, but it cannot close the last mile gap.
Right. Yeah. But exciting times coming up.
Yeah, that's true. Yep.
Okay.
Cool.
So if there's no more questions from the audience, maybe we'll go ahead and shut down. Do you have any other closing comments before we turn off the recording? Wait,
There
I
is
see
one
some-
question.
Let's see. You mentioned treating systems as a unit of intelligence, not models. If co-evolving AI isn't just a model, it's a system, then is your end goal to create a proportional unit of intelligence? Do you want me to read that again?
Yep, please.
Okay. You mentioned that treating systems as the unit of intelligence, not models as a unit of intelligence. So if co-evolving AI isn't just a model, it's a system, then is the end goal to create a proportional unit of intelligence?
If I understand the questions correctly, so the model is not the unit of intelligence, and the co-evolving AI is basically a combination of systems, not even just one system like what we just discussed before. I discussed with Craig. Your current components would be like, well, taking LLMs or synthesizing the data, capturing the knowledge. It could be one part of a system. There is another system where you have to like learn from the real world, or like there is a simulating environment. That could be another unit of intelligence where the system A or system B can interact, learn from it, can train, because it's a bunch of ecosystems. All this, each component that is contributing to this intelligence is actually a unit of intelligence. Like for example, oh, I need a real world environment. where I want to interact and learn from it. That could be one unit of intelligence, that deriving certain data from your real world. There is another one which is unknown, unterrain, that I want to learn. Like I want to learn from Mars. So in that case, we have to create a simulated environment that can help us to create that intelligence. So all these components will form the artificial intelligence that we are looking for.
Yeah.
So it's a system that's actually a one unit. There might be another system B, could be another unit of intelligence. All these components all the system can combined and integrated and work together that form the intelligence of level that we are looking for.
So simple answer, yes.
Yes.
Okay, and then the second question is, what are the technical challenges to consider when creating a co-evolving AI like this? And what are the ethical challenges? So technical challenge,
Ethical challenge. That's actually a great question. I can talk about ethical challenge. I had been in an ethical community in my previous work. There is always a debate between my colleague and myself. What is ethical in terms of AI? And of course, we need to have that. The example or analogy that I discuss is we are buying let's say there is a hardware tools that we are buying to operate a car, and if that hardware tools caused any damage to other humans, what should we do, and is it ethical or unethical? We can't even say that. Similarly, like if you build a system, if someone is trying to use that system in an unethical way, then how do we control it, or how do we prevent, or who we should blame, or who has to take the accountability of that messiness? So that's always still an unknown in this real world. So
and one comment on ethics, that's maybe 3 or 4 years old, I don't remember, but early when Amazon face recognition first came out, a lot of the models were trained on a public data set from YouTube that had labels of the people, and it happened to be related on a lot of Hollywood labels of, oh, this has this actor A or actor B. And so early when we talked about data drift, we talked about the model fitting the distribution of the data, but it turned out to be that face recognition model would also classify animals and other things, and it did the horrible thing of classifying some African Americans as apes, because their distribution of dark faces was so low. The people didn't know that. Is that, you know, they just grabbed a huge data set that might have 50,000 faces in it, but if you don't check for the distribution of things against bias, so your models are going to fit the data. If the data has bias, the models will have the same bias. Doesn't matter if it's vision or text or whatever your modality is. So that's something to be cautious of and ask questions of your training data. With respect to ethics.
That's true.
To ask questions.
And in another point with respect to ethics, I would recommend even every team must have like ethical team or ethical community to take the call on like if the model is really following all the ethics that we are following. So that governance is missing. I think large corporations might have that governance where they have following that ethical AI philosophy or like ethical AI principles. But for small and mid-sized companies or like team might not have this several dedicated ethic teams. And in terms of challenges with respect to implementing this co-evolving AI, there are several challenges here. The most important one is like having the knowledge or like capturing the knowledge about the real world and transforming it to the system and make the system can learn. That's actually the ideal problem that we are trying to solve here. And how to transfer that knowledge or have this knowledge stored in a way, it's not just embeddings. Like if you look at the memory layer or like whatever we are calling on embeddings, again, we are relying on another model or a foundational model that compress your data and give you a vectors. And if the embedding model is not good enough or not able to identify those individual signals, we are losing a lot of information in that memory. And same goes to like LLMs, a lot of hallucinations. If you retrieve the data back and run a RAG on top of it and summarize the content, what's the guarantee that it doesn't have like all the hallucinated data?
Yep.
So then we have to introduce a guardrails and ensure we are not producing hallucinated information, or we are not letting anybody else to abuse the system to use it in an unethical way. So the implementing the guardrails and preserving that knowledge and transform that knowledge back to the intelligence. And these are all some of the challenges I had seen. Another challenge is like collecting a feedback. Like, for example, we deploy the model and sales team will come and say that, hey, Gautam, there is a problem with this model. The customer is not happy. Oh, fine. What's happening here? So then either the technical team or a model developers might not be in the call with the customer, or even a customer cannot even transfer that what is happening, that information back to the model developer. Somehow the communication will get messed up. So 70% of the communication goes to product, and the product will transfer only like 50% to the engineer. Engineer will do another 20%. So it's basically like loss of information is happening. And most of these informations are captured in the meeting minutes. Even these days, we are using a summary like AI to summarize the meeting, and definitely it won't even pick on a unique signal that customers are looking for. I had seen that issue. So even if I see the meeting minutes notes, I still literally go through the meeting videos again and again to understand what's happening and what do they want. And of course, meeting with the team and stakeholders. So the cross-functional efforts is another challenge.
One thing with respect to ethics, when I was doing a worker safety project for construction workers, a lot of the data gathering was in the Middle East just because it was around oil and things. So they had one distribution of skin colors. But so one of the things I would try and do is capture the distribution of facial skin tones. And then if we're adding other data to it to be more world friendly, look at the world distribution of skin tones and then add some of that, especially if we're doing like synthetic data or we're getting data from other sources. So that way it can be more balanced to kind of a world level.
Yep.
But if some things for ethics, if you know at the time you're labeling your data or know at the time you're generating the data, what you want to check for error rates by, then you can check for error rates by issue X or issue Y, you know, whether it's male or female, young or old, whatever the issues are, you know, you need to measure something before you can manipulate it to improve it, to make it fair.
Yep. Yeah, that's true. Like, I think as a part of problem formation, so generally I start with the problem definition, ensure that every stakeholders, the model engineers, product owners, the ML engineers, even the sales folks, they are all understand on the same page. So the definition will clearly state what I'm looking for, what is my ontology will look like, and what is the performance will look like, and what will happen in terms of like the engineering metrics like latency, cost, all those information is defined and is communicated to their stakeholders. And once they stamped, yes, everything looks good, then we go and collect the data or like solve the problem. So that needs to be addressed initially before you even start that development work. If you don't have that the definition, then definitely like that down the line will a lot of problems will look like whatever happened with this face recognition system. Oh, what is the proportion that we are looking for in terms of finding the finding those biases? So all those details needs to be recorded and tracked, and feed the data back to your model development pipelines.
Sounds good. Any other audience questions? I think we've answered the ones that have been submitted. Okay, sounds good. Well, we've had some good questions today, a good presentation today. So thank you very much for your
Yep.
time.
Thank you, everyone.
And also mentioning the guardrails. So some of that will be covered in next month's meeting as
Oh,
well.
awesome. Yep. Awesome. Thank you, folks.
Okay. Thank you for your time, everybody. We're going to go ahead and close down this recording and presentation.
Thanks.
Yeah, and check our meetup site for the next month's meeting. So next month in November, we have two meetings on November 10th. And on November 15th, 16th, we have our PDS. So check our meetup site for details. Thank you again for your time, everybody.
And